All right, let's dive right into this explainer on the junction field-effect transistor, or as we all know it, the JFET. Today, we're going to translate some pretty complex solid-state electronics into a really intuitive journey. We'll start with the basic anatomy of this incredible device and work our way straight through to real-world circuit applications.
But hey, before we get bogged down in the mechanical details, consider this fascinating question for a second. How do you actually control an electrical current using nothing but an invisible field? We're literally talking about controlling a powerful flow of electricity without ever physically touching the current stream itself. It sounds a bit like magic, but as you'll see, it's just brilliant engineering.
So here is our roadmap for today. First, we'll meet the JFET. Second, we'll look at squeezing the channel. Third, curves and characteristics. Fourth, biasing for stability. And finally, number 5, the ohmic region.
Okay, section 1, meet the JFET, a new kind of transistor.
Now, you're probably already well acquainted with the bipolar junction transistor, the good old BJT. That's a current-controlled device that relies on both electron and hole current. But the field effect transistor, the FET, gives us a massive advantage. It's unipolar, meaning it operates with only one type of charge carrier. And even more importantly, it is entirely voltage-controlled. Because the voltage between two of its terminals controls the current, it offers incredibly high input resistance. That makes it a super efficient go-to device for a ton of low-voltage switching applications. Looking at the basic structures here, we've got the N-channel JFET on the left, which has two P-type regions diffused right into an N-type material, and the P-channel on the right, which is the exact inverse. Notice how the little arrow on the schematic gate points in for the N-channel device and points out for the P-channel. It's a really simple visual cue, but trust me, it will save you a massive headache when you're trying to read circuit diagrams. Moving on to section 2, squeezing the channel, the valve analogy. I always like to think of the N-channel as a literal water pipe, and the gate voltage as this invisible tightening clamp. You see, the JFET is operated with its gate source junction reverse biased. As we apply a negative reverse bias voltage to the gate, those white depletion regions you see actually expand. They physically squeeze the conductive pipe, increasing its resistance and powerfully restricting the flow of our drain current. So, what are the absolute limits of this pipe? To figure that out, we have to define the pinch-off voltage, or VP for short. If our gate-to-source voltage is perfectly zero, we can crank up our drain-to-source voltage up to a very specific point. The exact fixed value where that drain current maxes out and levels into a steady, constant flow, that is our pinch-off voltage. And at this point, the current itself is called IDSS, which is the absolute maximum drain current that specific JFET can possibly handle. On the exact opposite end of the spectrum, we have the cutoff voltage. If pinch-off gives us our maximum constant current, the cutoff voltage is the exact amount of negative gate squeezing we need to just completely pinch the channel shut. At this point, the depletion region has widened so much that the channel is closed entirely, dropping our drain current straight down to zero. Let's actually watch this dynamic in action. With zero gate voltage, boom, we get our maximum IDSS current. But as that gate gets more and more negative, the channel naturally narrows. Because it's starting out narrower, that pinch-off effect, where the current levels out, actually kicks in much sooner at lower drain-to-source voltages. Ultimately, when we hit that cutoff voltage, the drain current drops squarely to 0 amps. All right, section 3, curves and characteristics. Charting the flow. Check out this drain characteristic curve where the gate voltage is locked at exactly 0 volts. Notice how as we increase the drain voltage, the current rises proportionally. It's essentially acting just like a resistor here with this steep slope. But then we hit that magical pinch-off point, VP. From there, the line goes perfectly flat, giving us our constant IDSS current. It'll stay perfectly flat until we push the voltage so high that it violently hits the breakdown region, which is a great way to irreversibly fry your device. We definitely always want to operate safely within that flat, active region. Now, what happens when we start tweaking that gate voltage? By plotting multiple negative gate voltages together, we get this absolutely beautiful family of curves. Every time we make the gate voltage just a bit more negative, stepping from 0 down to negative 5 volts, the maximum constant current drops lower and lower. This graph is fantastic because it visually proves that the JFET operates primarily as a voltage-controlled, constant current device when it's sitting in its active region. Actually, if you take the endpoints of all those curves we just looked at and map them out, you get a transfer characteristic curve. The math behind this transfer characteristic isn't some straight linear line, it's parabolic. And this parabolic relationship is exactly why engineers playfully and very accurately refer to FETs as square law devices.
It's a totally nonlinear relationship governed by a squared mathematical term.
Because of that dynamically shifting parabolic curve, we get a crucial parameter called the JFET's forward transconductance, or GM. Think of transconductance as the JFET's ability to translate tiny little gate voltage changes into massive drain current changes. Down at the bottom of the curve, near cutoff, a change in gate voltage gives you almost no current change. But up near the top, closer to 0 volts, that exact same shift in gate voltage yields a massive jump in current. The device is just way more sensitive and powerful at the top of the curve.
To actually use this device reliably, we have to lock it into a stable operating position, which we call a Q point. That brings us to Section 4, biasing for stability, securing the Q point. So there are 3 main ways we bias a JFET to lock in that Q point. We usually start with self-bias, which is super common and simple, but its stability really depends on the physical quirks of whatever individual JFET you happen to pull out of the bin. If you need something tighter, you step up to voltage divider bias, which really smooths out the fluctuations between different components. And finally, if you need the absolute rock-solid pinnacle of stability, you go with current source bias. That setup forces the drain current to remain practically independent of the gate-to-source voltage. Visually, you can see how standard self-bias just uses that single source resistor at the bottom. That naturally creates the negative gate-to-source voltage by elevating the source above ground. Super simple and elegant. But when we step up to a voltage divider setup, we're adding a resistor network, R1 and R2, directly to the gate. This deliberately forces a much more predictable and stable voltage right at the gate, pulling our Q point tightly into line no matter what the JFET's specific datasheet variances might be.
And finally, Section 5, the ohmic region, the variable resistor. Take a close look at the very far left of our characteristic curves, right there in the gray shaded area. We're seeing something completely different here. Before pinch-off happens, the curves aren't flat at all. The current is rising with a relatively constant steep slope. Because voltage and current are rising together proportionally in this zone, the JFET isn't acting like a constant current source anymore. It's acting exactly like a standard resistor. If we intentionally design our circuit to drop the load line down into this specific area, keeping the current well below the IDSS maximum, the JFET sheds its constant current persona entirely. It transforms into a voltage-controlled variable resistor. By simply twisting a knob to tweak the gate voltage, we're changing the slope of the line. That means we are literally dialing the resistance of the channel up or down, completely without any moving parts. To wrap up this explainer, I'll leave you with this provocative thought. If we can replace a clunky mechanical potentiometer with its physical wipers and carbon tracks, with nothing but a solid-state, invisible electrical field inside a JFET, what other physical limitations of electronics are just waiting to be engineered away? Keep exploring, keep questioning, and I hope this provided a really clear path to understanding the incredible engineering behind the junction field effect transistor.